Hi there, I'm Stephen Kangasser, and along with Abhishek Shankar, we developed a digital demonstrator of a laser scanner for the BOLD Graduate Fellowship at Georgia Tech. Laser scanners are devices that use laser beams to create a 3D point cloud. The scanner sends out a laser beam and calculates the point cloud information based on the amount of time taken for the beam to return to the scanner. These point clouds can then be used to derive accurate information about the dimensions of the area being mapped. Laser scanners are widely used in the construction industry to capture details of existing structures and objects. Laser scanning is taught to building construction students at Georgia Tech, both at the undergraduate and the graduate level, with a cohort size of approximately 65 students. Despite having a large class size, the school is in possession of only 2 instructional laser scanners. This creates an impediment to the access of the equipment, which leads us to the problem we face. Courses often require students to apply theoretical knowledge through hands-on exposure to technology. When such courses are offered remotely, access to the equipment required to gain this exposure can impede the accomplishment of the stated course objective. Having a problem to tackle, we set out to gain more insight into how the knowledge transfer from the instructor to the students played out in the classroom. During our observations, we concluded that the instructors were also a stakeholder, as they were the ones providing insight about the equipment to the students. We observed several pain points, including instructional deficiencies where the instructor had to teach from a YouTube video to the class, a small screen size leading to students having to squint at the screen, and a lack of understanding of the effects of different resolution settings on scans. To elaborate on how we developed our solution, here's Abhishek with more.
To get a better understanding of how the laser scanner worked, we first mapped out the existing screen flow on the physical laser scanner to build a clear information hierarchy. This gave us crucial directions on where to best focus our efforts to translate the design of the older laser scanner interface into an interface in line with modern-day conventions and guidelines. The next step was to design an interface that would address the pain points we had observed during the need-finding phase. We went through a 3-stage iterative design process that involved building low, medium, and high-fidelity prototypes. Each iteration helped us address issues at varying levels of details. This helped add more clarity to our finished output. To address our pain points, we started off by increasing the screen size. This was done to not only fit more content, but to also allow breathing room for the existing elements, improving usability in the design. The improvement of usability was also a key driving force. Stylistically, the user interface was updated to match the newer models of the laser scanner. Modern interface guidelines, updated from Google's material design, laid the foundation for the graphical elements. Navigation conventions were also overhauled to match modern-day standards. All this was housed in a representation of a laser scanner that would mimic the authenticity of the physical experience. Another area of our focus was to address the needs of our 2 main stakeholder groups, the students and the instructors. For the instructors, we wanted them to have a demonstrator with which they can teach students the workings of a laser scanner. We also wanted them to have tools with which they could measure proficiency in the scanner operation. For the students, we wanted them to have the experience of having to work with the laser scanner whenever they wanted to. We also wanted to give them a way to assess their skill level in the operation of the scanner. Back to Stephen to see what we have in store.
Early in the design process, we determined that the best way to address the stakeholder needs was to incorporate 2 distinct operational modes, each of which is responsive to a unique use case. First, we have the access mode. The access mode is an unrestricted mode aimed at instructional and practice usage. This mode has full access to the digital demonstrator and has no constraints on the device settings. All of the laser scanner settings can be modified by the users. Instructors can employ the access mode as a teaching tool during class instruction. Students can follow along during a lecture, interacting with the laser scanner as they see beneficial. With the access mode, students can also follow up after a lecture, further familiarizing themselves with the laser scanner at their own pace. Next up is the assessment mode. The assessment mode is a restricted functionality mode aimed at enabling instructors to assess student proficiency in the operation of the laser scanner device. This mode can be used for evaluation at both the formative and summative stages of assessments. While in this mode, the user has a randomly assigned scenario that they must navigate. Access to settings not pertaining to these scenarios are restricted while in this mode. The assessment mode permits instructors to gauge the proficiency of students in using the laser scanner in one of the two randomly assigned scenarios. Students can use this mode to gauge their own proficiency and ability to operate a laser scanner device. When the student demonstrates operational proficiency in the digital demonstrator, they are rewarded with a data set identical to what a physical laser scanner device would provide at the successful completion of a laser scan activity. Students can then use this data set to advance to the data processing and analysis stages, which are outside the scope of this demonstrator. Our digital demonstrator has great potential as an educational tool. We believe that such a digital demonstrator can help make education accessible to more students. Students do not have to rely on the equipment being presented to gain an understanding of the material. Classes can be held remotely or asynchronously without students having to be physically present to interact with the equipment. This increases access to educational tools for those residing in remote locations, as well as areas where education might be underfunded. Now over to Abhishek to wrap things up.
Thanks, Stephen. Before we move on, let's take a quick recap of what we've covered so far. We came up with a problem statement, identified pain points and stakeholders, and worked to build a digital demonstrator with different use cases to meet the needs of students and instructors. So now that our solution has been developed, we plan on turning our attention to the broader impacts of such an open education tool. Specifically, we intend to explore the impact the digital demonstrator will have on universal learning. Initially, we will explore the impact the digital demonstrator might have on students with mobility limitations. We will also investigate the broader impact such an open education resource might have in improving the self-efficacy of these students and their perception of career opportunities in STEM. To learn more about the finer details of the interface and general troubleshooting tips, please visit the documentation which will be linked with the video.